Good morning. Previously we have studied about bridge rectifier with a capacitor filter that is giving a VDC. But this VDC is susceptible to ripples, line regulation and load regulation. Mostly all the electronic circuit require a constant VDC without ripples, without any kind of regulation. That's why we need a voltage regulator. It is an electronic circuit that provides a constant VDC even if the line voltage or load current changes, and this circuit is also going to remove the ripples. Read through the following four statements. Let us come back to the block diagram. The input to the block diagram is Vi unregulated and the output is V0 regulated. In between there is a control element. The conductivity of the control element depends on an error voltage VE coming from error amplifier. The error amplifier has two inputs, a constant reference voltage VR and a sampled voltage Vs. VE is directly proportional to VR minus Vs. Now let us look at the closed loop between control element, the sampling circuit and error amplifier. This closed loop enables us to have a constant V0. Any possible changes in V0 is compensated within that loop. Before getting into the circuit diagram of a BJT series voltage regulator, we need to recap on what we learned in the BJT at DC we did before. An NPN BJT need VBE equal to 0.7 to make it conduct, with base more positive with respect to the emitter. For a PNP BJT, we need emitter needs to be more positive with respect to the base. Then we also need a Zener diode to provide a constant reference voltage in its reverse bias. Let us see the first circuit diagram of a series voltage regulator. Let us try to compare it with a Zener diode regulator we learned in power supplies. In the normal Zener diode, there is a series resistance Rs between input and the output. In this diagram, we replace that series resistance with a BJT. Now let's try to understand what happens between Vi unregulated and VL regulated. There is a series voltage VCE with collector more positive with respect to the emitter. That means VL regulated is Vi minus VCE. But this expression may not help us mostly. Simple reason. VCE could be anywhere between 0 and supply voltage Vi unregulated. We need a more certain way of finding VL regulated. Let us look between the ground up to VL regulated. We can see there are two near constant voltages. Vz with the top part of the cathode of the zener with positive and anode with a 0 volt. Then we have base emitter voltage of BJT with base more positive with respect to emitter. Looking at the polarity, negative, positive, positive, negative. It is series opposing connection. Therefore, we can say VL equals VZ minus VBE. Now let's try to understand the current relationship. How do you find load current? The load current is VL divided by RL. And in this case, our load current is same as the emitter current of the BJT. We can find the base current of the BJT, which is emitter current, divided by beta plus 1. Now let's try to find out current through R. One end of the resistor has VI unregulated. Other end of the resistor is having a voltage of VZ. So the current through R or IR equals VI unregulated minus VZ divided by R. This IR split into two currents. The first one becoming the base current of BJT. The second current is going to be the zener diode current. Hence we can say IR equals IZ plus IB. We have made two modifications in comparison with original series voltage regulator. On the base circuit of Q1, we added another BJT Q2. The second modification is we included a voltage divider circuit R1 and R2 providing a V sample at the middle. This V sample or Vs is directly proportional to VL. We can also see this V sample is going to be same as Vz plus VBE2. Now we have two expressions for V sample. That is Vz plus VBE2 is V sample, and V sample also equal to VL times R2 divided by R1 plus R2. Equating two expressions for V sample, we can find an expression for VL. What is the benefit of this circuit? Looking at the third expression in the shaded area, we can see that VL could be several times bigger than Vz. Or in other words, by modifying the ratio R1 to R2, we could get any VL that you might need. The only condition is VL needs to be smaller than VI unregulated. Looking at the current relationship, current through R3, we need two voltages to find current through R3. One end of R3 is connected to VI unregulated. The other end of R3 is connected to the base of Q1. Once you find the load voltage, you add VBE Q1, you can find voltage at the base. So current through R3 is VI unregulated minus VB of Q1 divided by R3. We will see the calculation in the next slide. In a voltage regulator, what happens if there is a short circuit at the output? Naturally, in a short circuit, the load voltage must reduce to zero. But in a series voltage regulator, what can happen? There is a closed loop action trying to bring the voltage back to what it was before, which is a potentially dangerous situation that needs to be avoided. The modification that we do here is we add an R limit in series with the load current. We add an additional BJT. The base and emitter are connected on either ends of R limit. What happens here is when the load current increases beyond a certain limit, voltage across R limit exceed VBE of Q limit. Then Q limit is going to conduct and remove the current IR. In this case, the base current to Q1 is going to be reduced. The Zener diode current is going to be reduced. That means the entire operation of a voltage regulator is shut down.